Welcome to APA's weekly webinar. My name is Billy Zidek, Standards and Codes Administrator for APA. Just a couple of housekeeping items before we get started. The webinar recording will be posted to the APA web page later this afternoon. You'll receive a follow-up email in the next couple of days with a link to the web page where all recordings are housed, as well as a link to our upcoming webinar. We have webinars planned out for 2021 and some are open for registration. Professional continuing education credits and AIA CLUs are being offered for today's program. If you are an AIA professional requiring a certificate, please send an email to me at Billie, B-I-L-L-I-E, @apa.org, along with your AIA membership number if you have not done so in the past. All attendees are in listen-only mode. Please type your questions in the chat box and they will be answered in the order they are received. If we run out of time and we still have questions, responses will be sent directly to the person asking the question by one of our presenters. At this time, it's my pleasure to turn this over to Scott. Scott, take it away.
Thank you, Billy. Welcome to today's webinar on operational intelligence in a central heating plant. My name is Scott Smith. I am the industry principal for OSIsoft and focus primarily on critical facilities and data centers, which include universities, hospitals, airports, manufacturing, government, and data centers. I am just the host of this session today. What the lessons that we will show you today are regarding the University of Massachusetts central heating plant. On the screen, you will see the specific objectives, but for making sure you get the maximum value, the context of these lessons are how to leverage out of your second most important asset, and that is data. These lessons can apply to any individual challenge you face, from steam to chilled water optimization, thermal energy and dispatching, microgrid operations, to even solving basic challenges like meter data management or consolidating all of your data to drive sustainability objectives. Now, the most important asset at your disposal are your people. And so I would like to first introduce the sponsor who understands the challenges and the opportunities and where to look for and find value in the campus systems. Steve LeMay has been with the University of Massachusetts for 10 years next month as the plant manager. And prior to joining the university, he worked for 18 years with Mass Power, the last 10 years as the plant manager. I think all of us in the facility industry understand the challenges it takes to get funding and finance facility projects, especially projects around things like data and not physical assets. It takes strong thought leadership to get these implemented. And so Steve, thank you, and thank you for participating today. Next, I would like to introduce Priscilla Gamiero from Radix. Priscilla is a robotics and automation engineer and has been with Radix for nearly 5 years. Priscilla is the brains behind the scenes on how to implement and make Steve's vision a reality. She will present how we made this happen today. So again, Priscilla, thank you for your participation today. Now, let's get started. Steve?
Thanks, Scott. Appreciate that. So we are here at the, Priscilla, we can go forward. So this is really at the, we are here at the University of Massachusetts, Amherst, Massachusetts. Just to kind of let you know about size we are and things of that nature. So we have 1,300 full-time faculty members here, another 5,000 staff members. We have about 28,000 students here normally pre-COVID, and we've been growing at about 17% over the last decade. And part of that, we've spent about $1 billion here since 2004 in new infrastructure to support the new buildings in the campus, central heating plant being part of that project. So the campus growth facilities initiatives have driven an effort to decrease energy costs. Major losses really here are due to the buildings on campus, heating, cooling, electrical systems. So you can see the building energy use is really 85%. Steam distribution losses here about 6%. We do have 23 miles of steam and condensate piping out there in the campus, a lot of it in direct burial. And then we have in-plant use of steam for our deaerators and heat here at the buildings, about 9% there. So the campus peak steam load is about 333,000 pounds per hour. What happened to us in January, late January, early February. We can meet that campus demand with our HRSG steam heat generation recovery unit and 2 of our 3 package boilers. And for the electrical side of the house, the central heating plant, we can generate 16.5 megawatts of power here. Campus peak demand, 28 megawatts. That would typically happen in late August, early September as the students come back. Around that time, the CHP would be generating somewhere around 10 and 12 megawatts. But during heating season, we can generate 16.5 megawatts when we hit our peak steam loads. So what's inside of the central heating plant here? We have a solar gas turbine. So we exhaust that turbine into a heat recovery steam generator and then fire duct burners, and we can get about 100,000 pounds per hour steam out of that unit. And we back that unit up with another 600-pound boiler. This would be one of our 3 package boilers, all designed by Rentec. These all run about 125,000 pounds per hour steam. Once we surpass that steam, 220,000 pounds per hour of steam, we'll have maxed out that 2 megawatt steam generator you see there. And then we would bring on boiler 300 or 200, which operate at 200 pounds. And these will be supplemental steam for heating season. And we also have a 4 megawatt steam turbine on that. And from there we go to the campus through our 2 main steam lines. So we look at this facility as a microgrid. So we do have the central heating plant here, as you can see, providing all of the steam heats to the campus. We are also a major part of the electrical distribution for the campus. So we are considered the west side substation. We have another east side substation, all tied to our 16 megawatts, as well as 5 megawatts of solar generation, 2 big 2 megawatt parking lot canopies, as well as another megawatt of rooftop. And also inside of this, we have a 4 megawatt hour battery, which means we can store energy in this battery system and discharge it at a rate of 1 megawatt for 4 hours. Typically, we would do that in the late afternoon as the lights start to come on to reduce peak demand to the campus. And we're also connected to a 115 kV substation here, owned and managed by by the university. So this microgrid can be complex. So these will help us. On the next screen, we'll see a little bit of our electrical distribution breakdown. The campus will we can generate about 80% of the campus electrical needs over the years. Now that we've tied the east and west side together, we've actually got ourselves a little closer to 90%. Here you can see that 51%. This is from the 2019 data. So we have 50% came from the gas turbine, another 17% from the steam turbines, 5% from solar, and then the import from the east and west side. This comes up slightly under our 80%, but this was a project year. We were doing quite a few things, but normally we would run around 80%, and we recently improved to about 90%. So some of the business challenges really for us here as we start to look at this project, and what we're going to do next is, we have a fast growing student body. As we mentioned, we've increased about 17%, which has increased demand on the buildings for electrical and steam. And we have all kinds of data related to this that most of the campus would like to have access to, but due to cyber security concerns, we can't allow easy access to this data. And we've been working with professors and different individuals to try and give them access to the data so they can meet their projects at the same time maintain cybersecurity, which has proven challenging until recently. We do have a wide variety of controls, multiple networks, and we're all trying to bring this all together to drive a data-driven approach to optimizing operations here at the central heating plant. And then just to add a little more complexity, we have, as we kind of pointed out, what we have for equipment here, we have a lot of different equipment here. And then between the different configurations that we can run our equipment, as well as the weather really changes things for us here, whether we're in heating season, cooling season, the storm is coming, sub-zero tonight, 100 degrees the next day. And then we'll have the fuel prices are moving around at the same time. So we're continually trying to balance all of these things and give good direction to the control room operators, but we are looking for a solution that will help us make this easier for them to visualize our request, and so we could all see the same thing. That's really our business challenge. So the technical challenges come through that. Here we have Rockwell automation for our DCS, which runs with Rockwell software and a lot of Allen Bradley components out there, pretty much on everything. There's a PLC from Allen Bradley. And then our power management system is Snyder Electrical, independent of the Rockwell system, running lots of square D relays and interfaces. And we need to bring in data from outside, pricing data. So we'll bring from Eversource, who will be our local electrical distributor, as well as ISO New England, who we participate in the day-ahead market with. We need the real-time pricing because that drives our real-time pricing. And then all of the buildings on campus, the building management systems are going to be running through the Metasys system as part of Johnson Control System, which can be difficult at times to get data out of, certainly to visualize the data, we struggle a bit. And it's another one of those proprietary softwares that we have trouble interacting with, so we need a Johnson Controls person each time we come up on this challenge. And then Solar Gas Turbine, they run their own software for their gas turbine. We integrate to that so we can see that data. So all these different platforms and networks, we need to get them all to talk to tell the same picture or give the same vision. So the technical, the challenge here is to get that better visibility for us, but at the same time, dashboards for the building so that whether you're a manager, you're an engineer, you're a student, that you have access to data that's meaningful, that you can see and understand and use. We want to be able to predict the operational conditions based on optimizing cost and production given any configuration the facility may be in or current weather pattern that we're running through. And we do many requests from students they're writing a paper, they're in an engineering department, they want to know about the central heating plant, request a tour, and then after the tour, many data requests so they can write their reports. And we struggle to give them good data and meet all their needs and maintain cybersecurity in the past. So we want to identify all this data that we have and create, good KPIs that mean something and put them in an intuitive framework that people can use this data and it means something to them. Real-time fuel data, as we mentioned, we need this, and then operating the plant in the most efficient and economical way based on the different fluctuations that we have here, whether it's configuration or weather. It's been a challenge. So we went out for a competitive bid process to help us put together our vision of what we thought we needed based on what we just presented there for an energy command center. And after reviewing all of the information that we saw, we picked Radix as to be the person to help, the company to help us get through this solution. And based on the Pi platform, which I was a little bit familiar with, and the ease of integrating into other systems. So we awarded it to Radix, and we've been working with Priscilla ever since, and she's been a great resource, and she'll tell you what she's done.
Thank you, Stephen. So I'd like first to thank you all for listening to us today. And so I will divide the presentation in three main parts for the solution so can help you to understand what we implemented. So the first part is the question, how to integrate information from different systems, as Stephen mentioned, and calculate energy efficiency and create real-time KPIs. So first, before we move on about how we implemented, I want to just to put everybody on the same page about how the automation itself works. So basically, we have 5 layers, usually for the automation network. The first one is the sensors, where it's close to the equipment, where we measure, for example, for a pump, we measure a current, we measure voltage, we measure temperature, and other features. So moving to the next layer, the assets, it's where we combine the group of sensors, the set of sensors for the same equipment. And after that, we move to the plant. So now we start to provide more information about each equipment and more visualization for the operators and the manager. The next stage is when we have multiple assets and multiple plants. So we have like an enterprise where there is some directors or some managers that need to have more information, but more high-level information, as also Steven mentioned, about efficiency, about comparison between the last year, or even cost information. And next, and the last one is the community. So after we all implemented and developed this automation part for the plant, we want to deliver for the community more information about it. So moving forward, here we have two different architectures about the system that they could be done. The first one on the left is decentralized architecture, where it's more difficult to have information for all the sites and all the equipments that you want to access. On the right, we have a centralized architecture that is what we build in for UMass. So the features for this, the benefits of having a centralized architecture were, first, we have the empowering of operational experts. So now they can see more information. They can have multiple sources in the same place. Also, we simplify the operation data at scale. So it's more scalable to have those information centralized. Also, we can extend the data for different sectors. So even the community, if they have the rights to access the data, they will be able to access any information that they want to. And also keeping the asset intelligence and the capability to expand the operational data sets. So those are some of the features some of the benefits that we can have by centralizing an architecture. So explain a little bit what is PI system, because I know that some of you are not familiar with that. As Steven mentioned, we integrated with 4 different resources. The first one was OPC. The second one was Rockwell Automation for the most of the automation part. I mean, the major equipment such as turbines, boilers, all of them are integrated in the Rockwell system. Also, we have BACnet for the BMS, for the buildings and meters. And the last one was the pricing. So we integrate with the internet, the websites, all the pricing, so we can combine different informations to provide more insights about the plan. So using this interface connectors, that is a standard for a PI system, we have the PI server archiving all the information. And it's really good database because it's not only a database, but I will call the PI data archive for now like a database, just because they can archive more than 10 years of data. And as an example that I want to build with you, we have the tag. And here the tag doesn't mean anything. I don't know what is JFC, but in a second I will show you the power of the PI system. So the next layer of the PI system was the PI asset framework, usually called AF. And here we can see that we give a context for this tag. So the tag JFC that we didn't know about it, now just looking at the asset framework, we can understand that it's a discharge flow rate. So it's easier for the operator or even for a person that don't know about the plant to understand what is this meeting is about. So this is one of the greatest things that asset framework gives us the context for the plant. So we can model the entire plant by using the equipment, the assets, and their attributes. So moving forward, we implemented analysis that help us to aggregate more value for the measured data. So now not only we measure the information and storage the information, but we also do analysis. So for example, we calculated the pump efficiency, but we can calculate really complex equations using analysis. Next, we implemented the event frames, that is kind of alerts that help us to identify using different tags or different attributes. We can identify patterns or behaviors, bad behaviors for the equipment. Also using and combine all those 4 things together. So we implemented the context. Also, we put the analysis to aggregate more value. We create some alerts, and last, we notificate the operators and the managers that is something is happening. So the notifications can be through email or SMS. And now, for example, Steven, they don't have to be on the notebook or on the computer, in front of the computer, to understand that something is going on with the plant. So speaking about the pandemic world, this was a huge thing that we implemented before. So now everybody can have access even from home. Speaking about future integration, so the first integration that we implemented was the Pi Vision. With the Pi visualization suite, we could provide dashboards and KPIs using Pi Vision, but also we automated a lot of reports that before they are doing manually, and they took like 1 month to put all the information together. So now it's just being generated automatically. Also, the Pi system has possibilities to integrate with Pi Cloud service. Also, they have a set of Pi integrators and Pi system access, where we can access the system by programmatic, by integrating with Power BI, for example, and many other integrations that we want to. So showing you about the work that we implemented, the first one, the first screen that I would like to highlight for you was the CHP process visualization display. I like this display because in the first side, the first look, you may think, okay, this is just a new SCADA system, a new a screenshot for a SCADA system, and it doesn't aggregate anything for me. But looking at this display, I wanted to highlight that we have measured information for pressure, temperature, flow, but also we have boiler efficiency. If you look at the left, the top left, we have the temperature, we have the totalization for generation, energy generation, for heat input, and for consumption for gas, for oil, for LNG. So those informations are not measured. They are calculated in real time using Pi system. So as I mentioned, the operator now can look to one screen to make sure that the boiler is running as efficient as possible, or as they're supposed to be. Moving to this screen is more management screen. As I mentioned, we provide not only about process information, but also for a manager and directors. So here they have 3 different types of information. They have day ahead and full real-time fuel costs. As Steven mentioned, this is one thing that now they have historical information. So in 10 years, they can compare the price and the costs by the plant, but also they can calculate in real time how much they are costing to produce energy. And also they can decide when or not buy energy from the grid. Also here on the top left, we have also the cost to generate energy and steam. And here we have the comparison between the last year and the current year. So they can understand if the plant is running close to the last year, if it's more efficient, if it's less efficient, so they can control this information. Also on the right, we have the historical comparison between the months. So we have the average for the running gas turbine, steam turbines and boilers, so they can compare how much they are using for electricity and how much they are using for steam in real time. And also this is an interesting thing because they can share those dashboards with others that wanted to verify the information or other to follow the results. So it's a really informative screen. This one, the steam turbine, I bought because it was one interesting thing. They have calculated information, they have measured information, but here on the middle we have the design. So we compare in real time the design performance curve that the expected generation for the turbines and the current generation. So here in real time, the operator can see if there is any discrepancy or any difference, a huge difference, so they can alert. And also here on the bottom, you can see that we alert when we see loss opportunities. For example, if there is a valve that are open, but they should be open. So we alert the operator to make sure that he knows about it. So those are complemented things that we could implement by using the asset framework that is the feature for PI system. This is one of the dashboards that is around the campus, so people can understand better, as I explained, the community can now see the information and can understand, even if they don't know about electricity and how much is 11 megawatts, but they can compare with their homes or Tesla models or even iPhones, so they can have a notion about how much my campus is producing, how much the CHP is powerful. The last dashboard that I wanted to show you today was this steam meter alert. This one, it's one interesting thing because we implemented by combining the analysis, the event frames, and the notifications. So now in 24 hours, if the steam meter is stale, we alert the maintenance team to verify the meter. And before this system was implemented, they took almost 2 months to verify that the meter is really stale. So we reduced the time response, but not only that, we reduced maintenance costs as well, because now the team can go directly to the meter that is having some problem. Speaking about the second part of this presentation is how to address the impact of fluctuation in demand, weather, and fuel price, and combine those things together to optimize the operation for the plant. So we address this by doing the process and cost optimization. So we run an energy assessment to find useful information, to find gaps of energy usage, and to create an advisory system too that's helped the operator to keep the plant always operating at the maximum possible efficiency. So this assessment was divided in 3 main phases. The first one was the thermodynamic design, where we built the simulation by modeling the system inside the Thermoflex software. That is a proprietary software that we use to model the plants, and also to define the main process parameters. So the main equipment, the main seasons, and the main issues that that the operators are facing. Next, we did the engineering design, where we tuned the simulation by converging the equipment fit according to the vendor documentation and comparing with the real-time data. And last but not least, we did the offline design. So after we model, after we compare with the past data, we run different scenarios with the equipment to define when is best to run each equipment and when is best to run in at full capacity or at less capacity. So, okay, after I showed to you all the 3 phases that we did, so how we implemented it by using PI system. So the process was first to understand the operational scenarios. So we did by analyzing the historical data, the plant operation, and also the available instrumentation. and combined with the simulation model that we were able to build by running site surveys, collecting historical information, the equipment documentation. We also studied the operational life for each equipment and the thermodynamic design. So combine all those informations, we were able to build this simulation model and combine operational scenarios with the simulation model. We have the offline designs that I just mentioned as the third phase of the assessment. After we did this offline scenarios, we start to collect more information for live data. So we combine the live data for weather forecast, for photovoltaic availability, for example, the fuel price, real-time, day ahead, and contract by UMass, and the major efficient equipment that was calculated. So we combine the live data, fuel price, efficiency, the offline scenarios, and we provide a decision tree where the results of this decision tree methodology was the real-time advisory system. So explaining a little bit about the decision tree methodology, we studied the past 3 years of the plant to understand the main scenarios and the main inputs that change the configuration for the plants and change the rules to run the operation. And those are the ambient temperature, the steam demand, the power demand, the photovoltaic capacity that is free energy from the sun, and the fuel type availability and the price. So we combine all those information. We studied the ranges between them, and we come up with a decision tree with 5 levels. So those levels are really important because they choose which type of equipment they will be running and where or how is best to run the plant. So explaining how we implemented was combining this live data with the offline simulation from the thermal flow. So we storage this information, and we do some process efficiency analysis using the asset framework. Also combine the live data and put it together in the decision tree algorithm. Inside the asset framework, we got the advisory system with the dashboards and alerts. So the results that we got doing this this energy efficiency assessment was to develop a custom tool. Is totally customized for this specific plant to store real-time price information, but not only real-time price information. We put it the efficiency and other indicators. Also, we have the compilation for the usual operation configuration. So combining this with the simulation of the plant and with the store models that we did it on the thermal flow, we got about 150 scenarios simulated. That is just like on the picture on the figure on the right, where you can see all the equipments, the major equipments model inside the thermoflex. Also, we have an operation. We provide them the advisor system, so help the operators and the engineers to understand where is the real-time results for the simulation. And we also provide them a visualization that monitor the cost savings. So summarizing all the things that I mentioned, this is the screen that the operators see. So behind all the scenes, behind all the things that I just explained to you, the model, all the things inside the asset framework, we provide them a dashboard where we can see on the left, on the top left, all the current configuration in real time. We also have on the bottom the suggested configuration and the expected outputs if the operators runs the plant at the suggested configuration. Also, every time that we understand that there is a suggested configuration that is potential, we generate an alert for the operator to make sure that he acknowledges and he knows that he can operate the plant more efficient. Moving to the third part of this presentation is about the solution. So how we securely extract the information from the OT network to share into the IT network. As Steven mentioned, this is how about, okay, now we have all the data centralized, we aggregate value, we have an advisory system, but how we can share this information with the students, with other sectors of the UMass. So we use the architecture of the PI system that's they first for standard, they already limits the direction of the direct access to critical system, but they give some limits without losing the main thing, that is sharing the information. So what we use for data security topology was we have the data source and we connect with the PI interface in one direction. So the PI interface cannot command or cannot send any information for the data source, which allow us to provide this information outside the firewalls, but understand also that we are not compromising the security of the plant. So we use the PI interface to collect the information. We pass through a DMZ just to make sure that we are in a safe zone. Also, we historize and enhance all the information. So here in the PI server, we have the historical information, the analyze information is where they send the notifications, send the alerts, and also create more analysis for the system. And next, we have a new DMZ as well, and you have the delivery port. So between the delivery and the story enhance, we have a full two ways to communicate. So also, for example, we have the PI vision, and as I mentioned, they have the notifications and they have the event frames, that is the alerts, and the operators can acknowledge. So this is received by the PI server, and they can use that as well to compute more information, to store more information. So there is a two-way flow of information between the store enhance and the deliver. Also, on the delivery side, we have the PI Vision dashboards, as I mentioned. We have the PI data link for the reports, and the advisory system that I just showed to you, that it was a combination between the dashboards, the asset framework, and the event frames. Next, we have the reports. So just to exemplify a set of reports that we put it together to UMass. On the left, we have a meters report. So this is a report that they need to do every month, and later they need to do manually. Even the information that is already in the metasys, they have to go manually and put and fill this spreadsheet. So now it's all automatically. Also on the right, we have the early report, where it's a model of the report that usually UMass contract a company to provide those insights, and now they are generating automatically. So they don't need anymore to contract anyone, and also they can have access, for example, in the second quarter of the year if they want to. So they don't need to wait until the end of the year to start to know about the information. So moving to the results and the business impact that we got by doing this project, we divide those results in three main groups. The first one was the economic impact. So the first thing that we helped the operator was the make or buy energy decision by considering not only the multiple fuels on site, but also the live market data. So now they can have more insights about, okay, it's cheaper to buy from the grid, or it's cheaper to run the plant at the maximum capacity. So they have those insights because now it's all tied together in one system. Next, we have the suggesting the most efficient configuration to run the plant. So now all the operators have a standardized operation, and also they know that they're running at the maximum efficient as possible. Last, for the economic impact, we have the charge or discharge battery. So combine the ambient temperature and the cost of electricity and campus demand. we help them to know when they has to charge or discharge the battery. Moving to the operational awareness, we provide intuitive dashboards. I just show a set of them, but they have more than 20. Also, we provide them the energy production in real time. So now they have the totalization, they have the cost, all in one place. Also, we provide them the management dashboards with the results easily accessible. So before we implemented this system, some information are only available from the CHP plant for the computer inside the plant. And now, again, looking for a pandemic scenario would be really difficult to have everybody on the same place just for looking for data. And now it's all outside the firewalls. Also, we have the integration with many different systems. That it was a really challenge because each system speaks as a different protocol. So we need to make sure that we address all the information that we want to. And last, for operational, we create event frames that allows the maintenance team to be alert when the meter is offline. So as I mentioned, we reduce from 2 months to 24 hours of time gap. And last, we have the educational impact that Stephen mentioned as well. When a student or a researcher needs to have more information, more data, they now are available. They now can use the reports to extract information for their papers. And also they can use the the university's curriculum, and they can also use the plants as an example inside the during the classes. And last, we can display the production results to the entire campus. As I mentioned, we have some displays around the campus already showing the production. And now I will ask Stephen to summarize and give his impression about what was the project.
Thanks, Priscilla. So our goal really to collect, model, visualize all this instrument data, use the data to drive optimization efforts to reduce costs and meet the increased demand. And we've done an outstanding job there. I feel pretty good. The visualization of data has been huge. It's helped us in a lot of other ways to make it easy to give data to the campus, even something as simple as the solar data we used to have on dashboards going out around the campus. And that company is not supporting that anymore, so the data is gone. So with this system, we were able to recreate a dashboard fairly easy and give it to our IT folks and let them run it. And now that's pretty much what they're using for dashboards for everything. So these the challenges, the multiple data, dozens of configurations, fluctuation in the weather, and in system making decision makings and optimization. We really made great strides there. Visualization of data to the operations team has been very good, and the use of the tools have been outstanding. The use of Pi interface, the Pi vision screens is where all our dashboards are. It's how I can see the plant from home if I need to. That has been great. One of the things under there that sometimes we miss too that is the Pi data link. That tool is just an add-on to Excel and allows to pull data down for pretty much any tag, anything here on the campus, 1 minute, 15-minute, hour, monthly, and just drop it in an Excel spreadsheet so it can be easily be used by anyone on the management or engineering teams, because that's the way they like to see the data in Excel. So that's really been one of the biggest benefits of this, is being able to bring all this data in, put the same timestamp on all of it, and then be able to put it in an Excel spreadsheet or a dashboard for everyone to see. It's been outstanding for us, and really looking through what we promised to our accounting folks up there in Whitmore and what we've been able to deliver. We've saved about 3% of our fuel costs here at the central heating plant, saving the campus about $900,000 a year. So they appreciate that, and they appreciate the visualization to the data and the meter systems as well. It's been a huge help as far as bringing issues to people's attention in a timely manner and that affects the finance team immensely, and it's been great for us. So it's been a good project, and been glad to be part of it. And thanks, Priscilla, and the PI team.
Thank you. So I think we can open the
So-
floor for questions. Yeah.
So please take a moment to submit any questions in the panels. I believe to your right, we do have a flurry of questions for you guys to start with. And actually, one of the questions comes in, it's kind of near and dear to my heart, and that is around operator training. You know, we can make all kinds of systems, recommendations, and dashboards, but as humans, we're instinctual. We like to follow procedures and things we've done for the last decade. So what was the process, Steve, that you went through for operator training to help, you know, because if they don't make those adjustments, you don't get that savings. So what was that process? How did you go about that operator training, and what was the operator's response to this project?
So I think the operator's response has been outstanding. The training is, it's not been in depth. It doesn't really need to be. It's basically if we can use any of the Microsoft products that the guys are familiar with, or a web page, they're able to click around and find what they need to do here. So it's all good information available to them. They can't make a mistake with it, which I appreciate. And so it brings them data. But the drive for change is really the visualization. So we put a kiosk at the top of the stairs here coming into the central heating plant. It's available on the campus as well. But you can see the current plant configuration and the efficiency of the plant. So the team knows that we can see it, they can see it, and the campus can see it. So we want it to be the best it can be.
Thank you, Steve. There are a few questions on finance, and I won't put anyone on the spot on finance. And what I'll invite is, I would sure if you're a university and you'd like to speak to Steve, his information will be made available. I don't want to bring any financial information. They did share what they say, but anything beyond that, we'll leave up to the University of Massachusetts to decide if they want to share in a one-on-one conversation with you. One question here is, how long did the project take?
Yeah, so the project is going because we keeping adding more things. That is good. But the main thing was about 80 months. But we keeping adding more things. So now we are working on the water meters for identify some leakage and also to put it together. And also, as Stephen just mentioned to me, maybe there is some boilers, new boilers that we need to add for the system. So this I would say the project is keeping going because the CHP plant is growing as well.
Okay, thank you. And there's a question I'll add on to it, and it's like, I think you answered it with the water distribution. HVAC is a question, and I work with a lot of universities in similar projects as the University of Massachusetts. And one of the things I'll say is it's a journey. So typically what we find is the university starts with the primary project challenge or opportunity they want to solve for. Here, the optimization of the plant. And then from there, the data starts exposing. So I did an earlier webinar with Griffith University in Australia, and they focused on their utilities. And out of COVID, one of their major savings was water distribution. Basically, the lack of use of the facilities, will say, caused rubber valve and damper issues, and they had a lot of water leaks from the plumbing infrastructure. So again, I think it grows. I know University of Maryland's been a customer, and they started around situational awareness and cybersecurity, and they're into things around driving efficiencies and around HVAC in individual classroom spaces. So everyone has their own unique challenges. So I think it'll grow from there. Question, did the OSI software do the modeling, or did you model it in a different platform? Priscilla?
Yeah, so we modeled the plant in the ThermoFlow. The software is ThermoFlex, but the brand is ThermoFlow. It's a thermodynamic tool that we use to model. But after we run all the scenarios, we put the decision tree methodology or all the results for those simulations inside the PI system, and we did it all as users. So PI system just help us to install, and after that we manipulate the PI system to leverage their potential.
All right, thank you. One question, we'll be sharing the slides. The slides will be available after the session. Another question, what was the biggest technical challenge the combined team faced on the project?
I would, yeah, there is some. I don't know if Steven want to start.
Well, it's really just getting everybody on the same page and to commit to this platform and move forwards. But it was, you know, the initial interfacing and getting it all together, which was mostly handled by yourself. And now that people have seen that we can get all these systems to talk, they certainly appreciate the way it's configured now versus having another proprietary software that no one had access to, like Johnson Controls Metasys program. Having something that has an open platform like this where you can see everything that's happening and own that. So one of my big concerns up front is buying another program that I had to rely on somebody else to maintain and take care of, and going to the university and telling them that and making sure that they understand that this is not that program. This is an open platform. All of us can do this work, and we can just teach people what they need to be done, and there's no proprietary things happening in the background that we need to know and can only get a technician from OSI to work on.
Yes, yeah, from my side, I would say the same. I think to put all together all the different sources, this was the most challenge for us.
Okay, thank you. So Steve, I'll ask you this question. So I know you identified your business case and you outlined the savings you had at the end, but sometimes, you know, for universities specifically and public universities, money is always the challenge, right? Is there anything you can share on the business case or justification that really allowed you to make this project go forward? Do you remember that? I mean, it's been a while, but do you remember that, how you were able to convince to get to the point where you did meet your objectives and how you got this approved?
Yeah, I mean, and most of it for our business case is making this data, visualizing this data so everyone can see it. Before we did this, if you go to the control room operator and ask them what the average efficiency of certain things are, no one had any idea. Now they do. That was a big deal. Going to them and saying, my problem with meeting your request is that I don't have access to the Metasys system and I can't get that data out of there. And if I can get data, I can get a trend or something of that nature. I can't analyze that in Excel and help you. And everything that we have here has a different timestamp on it, and you want me to bring this picture together and give you good recommendations. I just struggle to get all the data together. So that was one of the things that I sold it on. I said, I just need to get everything in one historian with the same timestamp on, regardless of where the data is coming from, whether it's ISO New England, the battery storage, the PV, the building up there in the campus somewhere, or here at the central heating plant. So that was one of the big sells there, besides visualization and what I thought it could save you and make it possible for you to understand the data.
And just a question on the time, since COVID has been impacting all of our universities and facilities, has the output of the system affected your operations as you've had decreased demand with students and the things that are going on? And how has COVID impacted your campus specifically?
Well, the impacts of the campus are huge, as you can only imagine, with the reduction in steam flow, the reduction in water, and the reduction in resources to the campus. One of the things I think will help is there's a lot of reports that need to be done, and there's STEAM reports, and people struggle to visualize what's the effect of not having a campus, having people in that building or not having people in this building. And they'll go to the building automation crew, and they'll have to wait for something to come back to them. And I give them a screen. They can pull up all the steam meters. They can see them. They can see the trends. They can compare it to last year. They don't have to ask someone else to do it. It's available to them. They can see what we're off from last year to this year. or last month to this month. So it's easy for them to pull the data, particularly ones that they care about, which will be, the steam flow to the individual buildings. Every one of these buildings is running its own P&L out there, and they have a budget, and they want to know where they are, and they want to know how they're tracking, and they need to know, now, because everyone's asking them to give up some of their budget because we're going through a tough time.
No, thank you. I did just get another question. One of the concerns is every time you buy systems and, is the support and the cost. And how much support and daily interaction do you need from vendors to maintain this system? Or are you guys maintaining this yourselves? And is it, so how complex, or does it create a challenge for you like some of your other systems? How would you view that?
So I would say that the upkeep on it is not bad. We have the annual OSI license agreement, which is small potatoes. It's I think it's something less than $10,000 or in that range. But our IT department can do most of the maintenance. I currently do contract with Radix because we like what Priscilla's done here to maintain the system. So it's that is something we could do ourselves or have Radix do it, but they treat us very well and their price is reasonable, so we continue on with that. But if that relationship was to end, I think this is something that can easily be maintained in the house.
All right, and just give a last chance for any more questions while we're seeing if there's any additional questions. I do want to reach out and thank APA for allowing this presentation, and thank everyone today for their participation and listening. Again, we will be sharing the slides after the fact. This will be recorded if you want to share it with anyone. And we will make sure that the slides have the email address so that you can contact someone. And if there's no other questions, I'll just hand it back to you, Billy, since we're coming up on the top of the hour. And thank you very much, Billy. We appreciate your support.
We want to thank all of our speakers today and all of the attendees who took time out of their schedules to attend this webinar. And I want to wish everybody a very happy holiday. Until we restart our webinars in February, I hope everyone has a great rest of the year. Be safe, stay healthy. Until next time. Goodbye.